Welcome. Today we will be having our last lecture on planning. We already had taken 3 classes on planning, and we have looked at plan formulation and several algorithms for planning problems. We have looked at strips. We have looked at forward planning in the as search problem. We have looked at backward planning or regression, and in the last class we had looked at partial order planning. Today we will be having a look at another way of looking at planning problems, and we will introduce the concept of planning graphs and the algorithm graph plan. The instructional objectives of today's lecture is we will discuss the data structure of a planning graph. We will discuss the graph plan algorithm that uses the planning graph and describes an algorithm for finding a plan. On taking today's lesson, the student should be able to do the following. Given a planning problem, he should be able to construct the corresponding planning graph, and the student will also learn, given the starting from the planning graph, starting from the last state, how to extract a solution plan from the planning graph. Okay, so let us come to the motivation of today's class. As you have noted, a big source of inefficiency in search algorithms is because of the branching factor. If the branching factor was small, so if you are talking about either forward search or backward search, what makes search algorithms expensive is the branching factor. If the branching was 1 at every node, then the algorithm would be a linear algorithm. But otherwise, if the average branching factor is b and the depth of a search tree is n, you know that b to the power n nodes have to be expanded. So, to make a search problem more effective, what we would like to do is to limit the branching factor or limit the number of children of each node. When you look at backward planning, you start from the goal and you find all the actions that could have produced the goal state, and then from each of the previous nodes you do the same thing. The main problem is that you would be considering a lot of actions, and many of these actions may not be reachable, we may not be able to take the action starting from the initial state. So, our objective is to find out a subset of the actions which can be activated given the initial state that the agent starts from, and in this way we would like to limit the branching factor. This was one of the motivations for this algorithm. Now, one way to reduce the branching factor is as follows. First, you consider a relaxed problem. So, given the original problem, you take a relaxed version of the problem where you let go of some of the constraints, that is, you remove some restrictions of the original problem, and the relaxed problem that you get should be easy to solve, and the solution to this relaxed problem will include the solution to the original problem. So, once you get this relaxed problem, you can do a modified version of the original search, and you restrict the search space to only those actions that are applicable in the relaxed problem. Now, the basic idea of graph plan is you construct a graph that encodes some constraints on the possible plans. So, you take some of the constraints on possible plans and incorporate them to create a graph. And now, you will use this planning graph, which we will refer to subsequently as PG. We will take the planning graph PG to constrain the search for a valid plan. If a valid plan exists, so the way we will construct the planning graph for PG is as follows. If any valid plan exists, it must be a subgraph of this PG. So, a plan can be expressed in the form of the partial order plan that we have looked at is in the form of a directed acyclic graph or a DAG, and we will construct a planning graph such that a valid plan will be a subset of this PG. Now, we will show that the planning graph can be built in polynomial time, and once we build the planning graph, we are able to obtain restrictions on actions which will make the search for a valid plan easier. Now, a planning graph will be the planning graph that we will consider will be a directed graph. It will have several levels, and in this graph we will have two types of nodes, proposition nodes and action nodes. So, in the planning graph we have proposition nodes and then we have action nodes. And in fact, in the graph we will have several levels. The level with the proposition nodes will alternate with a level with the action nodes. And we will also have three types of edges between levels. There will be the precondition edges from propositions to actions. This proposition is a precondition for this action, or these two propositions are the preconditions for this action. These are called precondition edges. We have add edges from action to proposition. If this action is executed, this proposition will be added, and we have delete edges. If this action is executed, certain propositions will be deleted. So, this may be Q and this may be R, this may be not R. So, we may have delete edges, add edges and delete edges from action nodes to proposition nodes. We will have precondition edges from proposition nodes to action nodes. And in the planning graph, as we will see, the proposition levels and the action levels will alternate. The action level will include actions whose preconditions are satisfied in the previous level plus maintenance actions. So, suppose the propositions at a particular level will denote those propositions that can be valid at a particular state. In a state where certain propositions, a subset of these propositions will be valid, what are the actions that one can take from the state? The actions that one can take from the state are those for which the preconditions are satisfied. Also, certain propositions will get carried over to the next state by virtue of the frame axioms that we have discussed earlier. As we have noted that there can be many propositions in the world, and unless some proposition is explicitly added or deleted, the other propositions which hold in a particular state continue to hold at the next state. So, corresponding to these propositions, we will have maintenance actions or no op actions. Now, let us look at an example of the planning graph, and then we will go back and look at the algorithm graph plan. So, this is an example of a planning graph. This is the initial state or S0. These are the propositions which hold at the initial state. These are some actions whose preconditions are satisfied in this initial state. And this is the set of propositions that can hold in the next state. So, let P0 be the set of propositions that can hold in state S0, and let Pi be the possible set of propositions that can hold in state Si. So, this set is called Pi. Pi is the possible literals or propositions that can hold in state Si. This represents Pj. Pj is the possible set of literals that can hold in state Sj, and Ai are the set of actions that can be taken at state Si. This is an example of the planning graph. You see, this pink edges from a proposition to action means this is a precondition edge. Edges from an action to propositions mean that they are add or delete edges. They are add edges if they go to a positive literal, they are delete edges if they go to a negative literal. And these gray edges that we have, these edges, they are the maintenance actions or the no op actions. So, if the action, so this proposition continues to hold at the next state if the action does not add or delete them. So, this is an example of a planning graph. Now, so, in a planning graph, we have alternating. So, we come to the procedure graph plan now. So, let us briefly look at the algorithm for graph plan. In the algorithm for graph plan, there will be two phases. There will be one phase for graph expansion and there will be another phase for solution extraction. We start with k equal to 0, then k equal to 1 and then k equal to 2 and so on. For every value of k, we first do graph expansion, then we check certain conditions in the graph. If the graph meets those conditions, we do solution extraction. So, let us now look at the procedure for graph plan. In the graph expansion phase, we create a planning graph for a particular value of k. In the graph expansion phase, we create a planning graph that contains k levels. So, this represents a relaxed problem. That is, this planning graph that we get incorporates some of the constraints of the problem that we have, but not necessarily all the constraints. So, this planning graph is a solution to the relaxed problem, and the actual solution, actual plan will be a subgraph of this planning graph. Now, once we have created the planning graph up to k levels, we check whether the planning graph satisfies a necessary condition for plan existence. So, we will see what these necessary conditions are. Once we have the graph, we check first by looking at the last level of the plan whether this plan would satisfy a necessary condition for the final plan. If it does satisfy, then we try to extract a solution. If we succeed in extracting a solution, we output the solution. If we do not succeed in extracting a solution from the level k graph, we increment the value of k and then go through the graph expansion phase again. Okay. So, In the solution extraction phase, what we do is we consider only the planning graph that we have and we do a backward search from the goal state. So, in this backward search in the planning graph, we consider only those actions that are present in the planning graph, and this is what constrains the search space. Now, as a result of solution extraction, by backward search through the planning graph, if we find a solution, then we return the solution. And as we have seen earlier, this is an example of the planning graph. These pink edges denote the precondition edges and the add and delete edges. The gray edges denote the maintenance edges or the edges corresponding to no op actions. And Pi is the possible literals in state I, Pj is the possible literals in state j. So, this is the notation that we will be using. So, in a planning graph, as we see, there are alternating layers of ground literals and actions. So, at level I, at the action level I, we have all actions that might possibly occur at that time step, and at Pi we have all the literals that are asserted by these actions. So, in the planning graph, suppose this is the state level I minus 1, which consists of the propositions Pi minus 1, and suppose we have the state level I consisting of the literals Pi, and this is the action level I. Now, this is state level 0. These are the propositions which hold in the initial state which are known to us. These are precondition edges. So, this is an action. This action has this and this as the precondition. This action has this and this as the precondition, and these are the effect edges. So, these three are the effect edges and these are the precondition edges, and these gray lines correspond to maintenance actions, that is, this proposition is carried over to the next state if an action does not affect that proposition. So, how do we construct the planning graph? At level P1, we have all the literals which are given in the initial state. You know, in a planning problem, you are given all the propositions that hold in the initial state, and you are given a partial description of the goal state, and you are required to find a plan which achieves the goal state. So, P1 will include all literals in the initial state. Then we will add an action in level AI. So, suppose we have Pi, we will see how to construct AI. We will add an action in level AI if all the preconditions of that action are present at level Pi. We will add a precondition in level Pi if it is the effect of some action in level AI minus 1. So, a proposition will be added in level Pi if it is the effect of some action in the level AI minus 1. And because we also have these maintenance actions, we will carry over the propositions from Pi minus 1 to Pi using maintenance actions, and due to other actions we have some other propositions as effects which we will add to level I. In addition, so this is easy. In addition, we will maintain a set of exclusion relations called mutex relations. So, these mutex relations will be used to eliminate incompatible propositions and actions, and because of this mutex relations we will be able to reduce the graph size further. So, the graph consists of alternate levels. We have a proposition level P1 followed by an action level A1, then a proposition level P2 followed by action level A2 and so on. Okay. So, this is a planning graph. Now, what would be the mutual exclusion relations that we will consider? We say that two actions are mutex or two propositions are mutex, or so we have mutex relations between two propositions. We also have mutex relations between two actions. Now, two actions are mutex at some stage if no valid plan could contain both. So, if at a stage we find that both the actions cannot be together present in a valid plan, we say that those two actions are mutex. Similarly, at a particular level, if we find that two propositions cannot occur in a valid plan, we will call them to be mutex. So, now what we will do is, we will look at certain conditions under which we can label two actions as mutex, and then we will also find conditions under which we can label two propositions as mutex. So, we will study three different mutex situations between two actions. Two actions are mutex. We will consider inconsistent effects, interference and competing needs. First, we will look at what we mean by inconsistent effects. So, two actions A1 and A2 are mutex, they cannot occur together if an effect of one negates an effect of the other. Suppose the effect of A1 is P and the effect of A2 is not P. So, these two actions cannot come at this level of any valid plan. So, this is graphically illustrated here. We have a proposition level Pi, and here we have the proposition level Pi plus 1, and these are the actions. We say that action A1 and action A2 are mutex, which we denote by this line between them. A1 and A2 are mutex if the effect of A1 is inconsistent with the effect of A2. This could happen, for example, suppose Q is the effect of A1 and not Q is the effect of A2, and since Q and Q2 are mutex, they cannot occur together, then A1 and A2 will be mutex. So, this is by this condition is called the inconsistent effect condition. Two actions will be mutex if their effects are inconsistent. Secondly, we will say that two actions are mutex under the interference condition. That is, one of the actions deletes a precondition of the other action. So, this illustrates interference. Now, so we have these propositions at level I Pi, and this is Pi plus 1. We say action A1 and A2 are mutex if action A1 has an effect, let us say not Q, that is action A1 deletes Q, where Q is a precondition of A2. So, in this case we say A1 and A2 interfere. So, these two actions will be mutex. An example is the two actions stack AB and put down A. Now, put down A has holding A as precondition. Put down A has holding A as precondition, but stack AB is an action that deletes holding A. So, stack AB deletes holding A and put down A needs holding A. So, we cannot have these two actions together. So, they are mutex. Thirdly, two actions are mutex under the condition of competing needs. That is, if these actions have mutually exclusive preconditions. If the preconditions cannot occur together, then at the next stage we cannot have those two actions together. This is illustrated by the following diagram. Suppose we have these two actions A1 and A2. We say that A1 and A2 are mutex if their preconditions, suppose this is a precondition of A1 and this is a precondition of A2. If A1 and A2, so these two preconditions are mutex, then these two actions must also be mutex. For example, consider the action stack AB and unstack AB. Stack AB requires A to be clear, stack AB requires that B must be clear, and unstack AB requires that A must be clear. So, if these two cannot be clear at the same time, then these two actions cannot be executed in parallel. So, under the condition of competing needs also these two actions are mutex. So, we have three conditions under which actions are mutex. Two actions are mutex if they have inconsistent effects, if there is interference, or if there are competing needs. Now, let us see when two propositions are said to be mutex. Two propositions, but before we proceed, we see that these three conditions of action mutex, they can be found easily while constructing the planning graph. So, we can label these inconsistencies easily. It is also important to note here that these are only some of the mutex conditions, but these mutex conditions are easy to find and they put some restrictions on the planning graph, which goes towards reducing the amount of search that we need to carry out. Now, two propositions are said to be mutex if all ways of achieving the propositions are mutex. Now, when would we say this? So, for example, suppose one proposition is the negation of the other. So, P and not P are mutex because both of them cannot be simultaneously true at a state. Two propositions are also mutex if all ways of achieving them are pairwise mutex. So, this is illustrated by the following diagram. So, we have these two propositions that we are considering. We say that they are mutex if, you see, these propositions can be achieved by action A1 or action A2. This proposition can be achieved by action A3 or by this maintenance action. Now, you see, A1 is mutex with A3, A2 is mutex with A3, A1 is mutex with this maintenance action, A2 is also mutex with this maintenance action. So, these two propositions cannot be true simultaneously because you cannot achieve both of them simultaneously because all ways of achieving them are mutually mutex. So, there are two ways of achieving this proposition, there are two ways of achieving this proposition. So, there are two ways of achieving this proposition, two ways of achieving this proposition, and they are pairwise mutex. So, each of these two ways is mutually exclusive with each of these two other ways. So, this is a case of inconsistent support. So, therefore, these two propositions will be mutex. Now, let us look at an example to illustrate the construction of the planning graph, and then subsequently we will use the same example to run the graph plan algorithm. Now, this problem posed by Dana now is this. Suppose you want to prepare a dinner as a surprise for your sweetheart, and the initial state is as follows. There is garbage, hands are clean and it is quiet. So, garbage, clean hands, quiet is characteristic of the initial state, and your goal is to prepare dinner, have a present, and there should be no garbage. So, dinner and present and no garbage, this is the goal condition. And these are the actions which are available to you: cook, wrap, carry and dolly. So, cook is an action whose precondition is clean hands and effect is dinner. Wrap is an action, its precondition is quiet and effect is present. Carry is an action which has no precondition and its effect is no garbage and not clean hands. So, hands become dirty, but there is no garbage. Dolly is a action which has no precondition, its effect is no garbage and not quiet. So, we have these actions cook, wrap, carry and dolly, and with these actions we have to see how we can achieve this goal of dinner and present and no garbage. So, this table just has the same thing, this action, a precondition and the effect. Cook has clean hands as precondition and dinner has effect. Wrap has quiet as precondition, present as effect. Carry has no precondition, no garbage and no clean hands as the effect. Dolly has no preconditions, no garbage, not quiet is the effect. In addition to these 4 actions, we also have all the maintenance actions, so 1 for each literal. So, now let us see what this signifies. The initial state we have garbage and then clean hands, quiet. And you also know whatever propositions are not mentioned in the initial state are assumed to be absent. So, in the initial state there is no dinner, no present. Now, what are the actions that one can carry out in the initial state? One can do carry, one can do dolly. Carry and dolly have no preconditions. One can do cook, the precondition is clean hands. One can do wrap, the precondition is quiet. And the effect of cook is dinner, effect of wrap is present, effect of carry is no garbage and no clean hands, effect of dolly is no garbage and not quiet. Now, let us see what sort of mutex hold between the actions. So, in addition to these 4 actions, we also have the maintenance conditions, 1 for each literal. For example, garbage to garbage there is a maintenance action, clean hands to clean hands there is a maintenance action, quiet to quiet, similarly no dinner to no dinner, no present to no present, these are maintenance action. Now, we notice that carry has no garbage has the effect, and the maintenance action corresponding to garbage has garbage as the effect. Since garbage and no garbage are mutex, they cannot occur together. So, carry is mutex with this maintenance action. So, carry and this maintenance action are mutex. Similarly, dolly has no garbage as the effect. This no up has garbage as the effect. So, dolly is also mutex with the maintenance action. Now, wrap, so not quiet. So, Dolly has an effect of not quiet and quiet has the effect of quiet. So, since not quiet and quiet are mutex, so Dolly cannot occur along with the maintenance action quiet. So, Dolly and quiet are mutex. Dolly is mutex with wrap because wrap requires quiet and Dolly has an effect not quiet. This is an example of interference. Dolly has effect not quiet, wrap requires quiet. So, Dolly and wrap cannot occur together. Not quiet is inconsistent with present. Cook is inconsistent with not present maintenance action. Wrap is inconsistent with not present maintenance action. So, we start with the initial state garbage, clean hands, quiet, no dinner, no present. And these are the 4 possible actions: carry, dolly, cook, wrap, and these are the maintenance actions. And then we find all the mutex relations between these actions according to the 3 rules that we have looked at. And by them, carry is mutex with this maintenance action for garbage, dolly is mutex with the maintenance action from garbage, dolly is mutex with wrap, not quiet is mutex with present, cook is mutex with not dinner, wrap is mutex with not present. So, at state level 0, we have all the propositions or the atoms that are mentioned in initial state union the negations of all atoms which are not in S0. At action level 1, we have all actions whose preconditions are satisfied in S0. In state level 1, we have all effects of all the actions in action level 1. So, this is how we can construct the planning graph, and by looking at the mutex conditions, we can specify the mutual exclusive relations between them. So, we have this. So, here I have not put the maintenance action for not dinner and not present, but the rest we have this 2-level planning graph for this problem. So, the actions as we have noted are carry, dolly, cook and wrap. These are the precondition links. These are the precondition links and these are the effect links. Okay. These are the maintenance actions and then we have specified the mutex relations between the different actions. Okay. Now, we already saw how to have the mutex relations between the different actions, and then we can also have mutex between the different propositions. So, this is easy. Garb is mutex with no garb, clean hands is mutex with no clean hands, quiet is mutex with not quiet. Then dinner is mutex with not clean hands, because dinner so dinner requires clean hands, and so dinner is mutex with not clean hands. Present is mutex with not quiet, because present requires quiet. So, these are the mutex relations between the different propositions. Now, once we have this planning graph where we have state level 0, action level 1 and state level 1, now we need to check to see whether there is a possible plan of length 1 through this planning graph. So, the goal is not garbage, dinner and present. We see all these 3 propositions are present in the goal, and we want to see if a plan exists. Now, not garbage, dinner, present, all are present in state level 1, they are not mutex with each other. So, this satisfies a necessary condition that a plan can exist. Now, we have to do plan extraction to find the solution. Now, how do I find the solution? You see, not garb requires either carry or dolly. Dinner requires cook, present requires wrap. So, for present we have to take wrap, for dinner we have to take cook, and for not garbage we have to take either carry or dolly. Now, carry is mutex with cook. So, we cannot take carry, then we have to consider dolly. Dolly is mutex with wrap, so we cannot take the action dolly. So, in none of these ways we can satisfy the not garb action. So, you see, this plan cannot be extracted from starting from this planning graph, because not garb can be achieved in two ways, carry and dolly, and carry is mutex with cook. Cook is required for dinner. Present can be only achieved by wrap, and wrap is mutex with dolly. So, neither carry nor dolly can be executed, which is consistent with these two. So, neither of these work, and so we have to abandon this plan. So, this plan does not exist. Now, what do you do if this plan does not exist? Now, you have to consider expanding your planning graph further. So, you have to go back and expand the graph further to one more level. So, we generate one more action level. So, we had already generated up to this, we generate one more action level 2, and then state level 2. And then we again try to see if state level 2 satisfies the necessary conditions for plan existence, and then we try to extract the plan from state level 2. Now, so this is the planning graph expanded up to state level 2. Now, here we see that the carry, dolly, cook and wrap actions are there, and we have found all the mutex relations between the 4 actions. We have found the mutex relation between the propositions. Now, before we proceed further, let us look at certain observations. So, a first observation is that the set of propositions in state level, these are the set of propositions in state level 0, these are the set of propositions in P1, this is P2, P3, and we observe that the set of propositions are always monotonically increasing, the size of this set is increasing. We also note that the proposition mutex relationships are monotonically decreasing. Whatever mutex relationships we had initially, as we proceed further, these relations can be dropped. No new mutex relations will arise. Observation 2 is that the number of actions, the set of, since between two levels, the number of propositions is increasing. So, the number of actions which are applicable will also increase. So, more actions will be applicable here than in this level. So, the number of state variables are increasing, the number of propositions are increasing, number of actions are increasing, and then the mutex relationships between the actions are decreasing as we go. And from this we can conclude that as we construct different levels of the planning graph, after some time the planning graph will level off, because we are always increasing the propositions. After some time we cannot increase any more propositions. So, the propositions that we had at level I will be the same as the propositions that we will have at level I plus 1. So, after some time we will find that all the levels are identical. So, because we have a finite search space, the set of literals will never decrease and no new mutexes will appear. So, this means that after some time our planning graph will reach a saturation point. So, the planning graph cannot go on forever. Now, let us see what is a valid plan. A valid plan is a planning graph where actions at the same level do not interfere. Each action's preconditions are made true by the plan and the goals are satisfied. So, as we have noted, a valid plan is a subgraph of the planning graph that we have, and it is that subgraph where the actions at the same level do not interfere, that is, they cannot be mutex. Each action's preconditions are made true by the plan and the goals are satisfied. Now, in the graph plan algorithm, as we have noted earlier, there are two phases. The first phase is grow the planning graph. This is called the graph expansion phase. And then we have the solution extraction phase, where we search the planning graph for a valid plan. Now, if I do not find a valid plan, we will add one new level to the planning graph and try again. Now, before we proceed, we note that the creation of the planning graph is a polynomial time algorithm. The size of a t level planning graph and the time to create the planning graph are polynomial in the following. T is the number of levels, n is the number of objects, m is the number of actions, and p is the number of propositions in the initial state. And the size and the time of this planning graph is proportional to p plus m into L into n to the power k. So, for k constant, this is a polynomial. Their maximum action nodes are m into n to the power k, where k is the largest number of action parameters that we can have, and k is usually constant. K is the number of actions in the possible actions in the planning problem that we are considering. Now, let us look at, once we have got the graph, let us look at how we do solution extraction. So, for solution extraction, we do a search for a solution plan by backward chaining on the planning graph. We first start at the last level of the planning graph where the goals are present, and we try to achieve goals level by level. At level k, we pick a subset of non-mutex actions that can achieve the current goals. Their preconditions of these actions become the goals for the k minus 1th level. We build the goal subset by picking each goal and choosing one of the actions to add. And then it could be that one action achieves two different goals. So, if we had a goal G1 for which we chose action A1, and if G3 is also achieved by A1, then we can achieve G3 by A1, and then we continue on the remaining goals until we find a solution. If we do not find a solution, we backtrack and find the alternate, we check the alternate ways of achieving the unachieved goals. So, in the plan graph search, we have basically going in a loop. If goals are present at the current level and they are non-mutex with each other, we choose action to achieve each goal and add preconditions to the next goal set at the previous level, and then we continue recursively until we find a solution. So, this is what we execute in the different phases. So, this is an example of a planning graph where suppose this and this are the goals, these two propositions are the goals that we must satisfy. And as you note that this proposition can be satisfied either by executing this action or by using this maintenance action. This proposition can only be satisfied in one way. So, we must take this action must be selected, and out of this action and the no op, we have to select one of them. So, this is the state, this is the planning graph that we start with, and this is the planning graph that we start with, and corresponding to these two possibilities we get two different planning graphs. In this planning graph we have chosen this maintenance action to satisfy this goal, and in both the planning graphs we choose this action. In this planning graph we choose this action to satisfy. So, in this planning, in this side of the search tree we have taken these two actions, here we have taken only this action. Now, in this case at the previous level we will require these two conditions to be satisfied. These two conditions are the preconditions of this action. In this case where we have this maintenance action for this proposition must have been true at the previous level. So, if we choose this maintenance action, these are my goals at the previous level. On the other hand, if I choose this action to achieve, here I have these two actions to satisfy. This action has these two as the preconditions, this action has these two as the preconditions. So, here I have to satisfy these four preconditions. So, this is my goal at the next level. Now, for each of these cases we will again consider these new sets of goals and try to see how we can achieve them. So, this is taking the previous example where we have these three preconditions, and for this precondition we have only this maintenance action. For this proposition this is the only action that achieves this proposition. For this proposition this is the only action which achieves this proposition. So, we take these two actions and then we find, in order to do this at the previous level, these three propositions are required. So, we get the goal at the next level, and thus we proceed until we come to the 0th level. If the propositions that we get at the 0th level are a subset of the initial state description of the system, then we have achieved a plan. If we do not achieve a plan, we backtrack and we explore other portions of the search tree. Similarly, from the other side we will have some more other goal, and then thus we will proceed. Now, how does, so graph plan proceeds like this. How long will graph plan proceed? Graph plan will only, after some time graph plan will find that in the graph expansion phase at level k the propositions that we have got is the same as what we get at level k plus 1. At that time we have reached saturation and we cannot expand the graph any further. If we have not found a solution, we stop. Also, graph plan can record the sets of unsolvable goals and which can make it more efficient. So, to repeat, for solution extraction, in graph plan G is the set of goals that we need to achieve and J is the level of this current state Sj. If J is 0, that is we have reached the initial state, we return the solution. Otherwise, for each literal L in G, that is each proposition which occurs in the current goal, we non-deterministically choose an action to use in state the previous state as j minus 1 that achieves L. Now, once we have chosen actions for each of the literals in the goal, if any pair of chosen actions are mutex, then we backtrack. Otherwise, we get G prime, which is the set of preconditions of the chosen action, and then we recursively call solution extraction on G prime and j minus 1. So, this is the solution extraction algorithm, this is the search algorithm, but this search algorithm is constrained because the planning graph incorporates constraints on the problem. So, let us come back. Now let us come back to the planning graph that we obtained. Now, in this planning graph at level 2, we find that the actions not carb, dinner present. these are present. So, we try to find the solution, and then in order to find the solution we see that there are 3 ways to achieve not garbage: carry, dolly and the maintenance action for not garbage. For dinner there are 2 ways, the maintenance action and cook. For present there are 2 ways, the maintenance action present and wrap. Now, we choose a way of achieving not garb by carry, we choose dinner to be achieved by the maintenance action dinner, and we choose present to be achieved by the action wrap. So, this is one possibility by which we can achieve these goals. Now, in order to do this, for wrap we have the precondition quiet, for dinner we need the precondition dinner, for not garb there is no precondition. So, at the next level we have quiet and dinner as our goals. Now, to achieve quiet and dinner, quiet is achieved by the maintenance condition quiet, dinner is achieved by the action cook. Cook requires clean hand as a prerequisite, quiet requires quiet as a prerequisite. So, clean hands and quiet are required in the initial state. Now, clean hands and quiet are satisfied by the initial state description of the problem, and therefore, we have found a plan. So, this plan, as you see, this plan which is given in blue is a subset of the planning graph. It is a partial order plan which is a subset of the planning graph. Now, how does graph plan compare with partial order planning? So, graph plan creates because of the constraints that the graph plan imposes on the search space, it is faster than partial order planning. So, before we end, I would like to give you an exercise to try out. So, the domain that we will be considering is a rocket domain, where we have the following actions: move r x y, move rocket r from x to y, precondition is at r x and has fuel r, effect is at r y and not at r x and not has fuel r. The second action is unload C r x, unload cargo from rocket at x, precondition in C r and at r x, rocket is at x, cargo is in r, effect not in C r and at C x. Third action, load C r x, precondition is at C x and at r x, effect is not at C x and in C r. So, we have 3 actions: move rocket from x to y, unload cargo from rocket r at x and load cargo in rocket r at x. Now, given this problem, we have to apply, you need to apply graph plan to this domain with the goal cargo B and cargo C are in Delhi. This is your goal. Initial situation, cargo B and cargo C are in Kolkata and rocket R is in Kolkata and R has fuel. So, for this you have to execute graph plan, and on the same problem you execute partial order planning. So, we stop here. Thank you.